Good afternoon, students. Quickly log in, Nana. Very good afternoon. Okay, Nana. Last class we are concluded the class with stability, diagonal runaway, as well as how to construct a CE amplifier stage. So there's a need of stability. So what are the bias compensation techniques that all the topics we have covered in the last class in today's session. So let me move to our next topic is small signal low frequency transistor amplifier models. Now, so in the last class we have just analyzed the DC analysis and we have just not applied any AC signal to that, and we just fixed the operating point. Thereafter we applied here AC signal. Now let me move to our AC analysis by applying an AC signal in addition with the DC sources. So now those DC sources are applied to the transistor in order to put the transistor in linear region, and in order to act like an amplifier. A transistor can act like an amplifier if I apply a forward bias at the input junction and a reverse bias at the output junction. Then only your transistor is operated in the active region or in linear region. If the transistor is operated in linear region, then the transistor can act like an amplifier. Now, so what is the need of an amplifier? So that we are going to discuss now. Here, if my input signal, your AC signal is a weak signal, so which cannot produce the small, which cannot produce your large fluctuations at the output. So now, if you are having a small signal input signal, then it will provide a small fluctuations in the collector current in comparison to the quiescent values. And the amplifier is called so small signal amplifier or a voltage amplifier. So now if I'm applying a weak signal for the amplification and that small signal or a very less voltage levels, if I'm applying an AC signal, so then those signals can give smallest fluctuations at the output collector current in comparison to the DC voltages what you applied on your amplifier. So now these signal, the input signal, AC signal magnitude, when I compare with the quiescent value, it is very less. And such type of, if I am applying such type of weak signals as an input, then that amplifier is known as the small signal amplifier or the voltage amplifier. And these voltage amplifiers are used as the first stage of an amplifier. In radios you can use it, as well as in TV receivers, in tape recorders, as well as in the stereos, and wherever the measuring of any physical quantities are required. So in measuring instruments also we can also utilize here. Measuring instruments also we can use here amplifier or a voltage amplifier or small signal amplifier. Now these amplifiers consist of a transistor, so which operated in active region, and that can amplify the smallest or the weakest signal. Hence, it is named as a small signal amplifier. Now, it is desired that the amplifier will be operated in linear. So then our output collector current will vary with your input current, base current IB. So now, so in order to analyze this circuit, we are moving to the hybrid parameter mode or H parameter model. So to analyze your small signal analysis, we are moving to the H parameter model for a low frequency analysis of BJT. Next, now let me first move to our basic operation of your amplifier and what are the parameters that you can calculate from its characteristics of an amplifier. Now, so this circuit, so whatever the image in this slide shows the common base configuration amplifier or common base amplifier. Simply we'll call it as a common base amplifier since my base is a common here from your input to output and I apply the AC signal. Now, so it's simple. It is a simple circuit where this simple circuit resembles like your common base configuration. So now this common base configuration, but instead of you have in your common base configuration, you only have the DC voltages which are applied at the base junction, base to emitter junction as well as to the collector to base junction. But now, so in order to construct an amplifier, common base amplifier, we added one more AC signal source. We have applied an AC signal which is VI at the input terminal. Now in a common base amplifier, your input terminal will be your emitter. So now in order to apply, so here VI is coupled at the emitter, right? Now, so here the low resistance will provide at the input circuit since it is in common base configuration where the base current is very less here. So now our input current is equal to so VB divided by the ratio of VB to IE. So here the amount of current IE is more, hence the resistance is IE is more, hence the resistance input resistance is very less. When the input resistance is if you have the input resistance is very less, so next the current amount of input current is high. So and that will be transferred to the output junction and we collected that output collector current IC is equal to so IC is equal to alpha times of IE plus IC below. So now so alpha is the amplification factor of your common base amplifier stage. Now so the emitter current caused by the input signal which contributes the collector current and we'll collect that collector current across the load resistor RL and will collect the output voltage. A large amount of voltage will be dropped across your load resistor RL since IC is high. So now here what is the amount of voltage we can have at the output is VCE is equal to VCC minus of IC RC. VCE is equal to here we have a output collector so common base configuration. We have the output voltage which is VCB, so which is equal to VCC minus of IC into RL. So now if IC is high, so amount of drop across this RL become large, then VCB is very less. So now here output voltage is less whenever the collector current is maximum. Since our input current is high, so output collector current is alpha times of your IB. Hence here IE. So hence here the amount of voltage drop across your collector to base junction is minimum. Now a small input voltage. Now if I am changing a small input voltage at the input of your emitter at the input, so that may lead to your a large amount of output voltage. So now so let me first take an example. Now I changed my input voltage with a a small change in the input voltage with a magnitude of 0.1 volt in the input, and that being applied to the common base amplifier, then which further produces a change in input current with a magnitude of 1 milliampere as the emitter current. This emitter current will produce the change in collector current. Now, as we already know that our collector current approximately equal to the emitter current in your common base configuration. Hence here the collector current is also equivalent to 1 milliamp. So if the load resistor is 5 kilo ohms, then amount of voltage drop across that load resistor is equal to 5 volts. So if the load resistor value is 5 kilo ohm and the amount of collector current when it passes through that load resistor 5 kilo ohm and amount of voltage drop across that resistor is 5 volts. So now hence it is observed that a small change in 0.1 volt in the magnitude of your input can cause a large amount of output voltage with a magnitude of 5 volts. So which means a voltage level of the signal is amplified. So hence here, so this configuration with the additional AC signal, with an additional AC signal is known as a voltage amplifier. So now this configuration with an addition, the CD configuration with an additional AC input signal is known as the common base amplifier or your voltage amplifier. Now Okay. From which slide are you not able to listen? You want me to repeat it? There's a network problem. After connecting that, I didn't check my mic, so it is in the ready state. Sorry for that. So just go through this first slide. Actually, today we're going to learn about your transistor as an amplifier. Now, till last class, we only discussed about the applied after applying your DC signals. So, what is the response of your amplifier? DC analysis we have done, and we have not provided any AC signal. So now, from this slide onwards, or from this session onwards, so we're going to apply your AC signal for the amplification. So in addition with your DC signals, so those DC signals were used to operate your transistor under active region or in the linear region, which sets your operating point on the DC load line. Now, in order to have the faithful amplification, so we have to provide the stability using these DC signals, the DC voltages, whereas AC signals are used to amplify the weakest signal and that will be available at the output as an amplifier voltage signals. Now, so the weakest input signals when you apply as an AC signal to the input, so at the output we will have a amplified output voltages, which is in the form of voltage. Hence, so these are known as voltage amplifiers or small signal, so which can amplify the small signals. So if I connect a small signal inputs, that can amplify those small signals, hence it is known as a small signal amplifiers or the voltage amplifiers. And these voltage amplifiers are used as the first stage of the amplifiers. So in a multi-stage amplifiers, so we are going to utilize this voltage amplifiers are the first stage amplifiers, and these are used in radio communications, in TV receivers as well as in tape recorders and in stereos as well as in measuring instruments in to calculate your physical quantities. Now, this amplifier consists of a transistor which is operated or which is biased in active region so that the transistor can act like an amplifying device. Now, the output signal is linearly proportional to the input signal so that the output of your speaker of an amplifier, if I connect a speaker at the output of your amplifier, is exactly the reproduction of the signal which is generated. Right. Now, it is desired that the amplifier to be linear one. So, in order to act like a small signal amplifier, so your amplifier must be a linear one. And in order to analyze this small signal amplifier, we have to do the AC analysis. Now, that AC analysis will be calculated by using a small signal H parameter model. Now, here in your amplifier, first let me move to your post CB amplifier. So now, common base amplifier I am taking. So it's nothing but your common base configuration. So here, just to see a base is common and we have an additional DC voltage sources VEB and VCB. Now this VEB and VCB can operate your transistor in linear region. So now VEB is the input junction voltage, DC voltage we are applying, and VCB is the output junction voltage which makes your output junction reverse bias. Now this is the small signal input source what you connected at the input of your common base amplifier. Now here our input resistance is very less in your common base configuration since VI, the low resistance, because since it is the amount of emitter current is high. So when amount of emitter current is high, the input resistance becomes low. So now the emitter current causes the input signal which contributes a collector for the output current. So then, so the flow of your collector current through the load resistance can give you a large amount of output voltage drop across your load resistor RL. Thus, a small change in input voltage can give the large amount of output voltage. Hence, these amplifiers are known as the voltage amplifiers. Next, let an example I am taking. So we have a change in input voltage at your emitter with a magnitude of 0.1 volt in the input voltage. Now, which produces a change, change in input current of IE is equal to 1 milli. For example, for a 0.1 volt of change in input, we have an input current of 1 milliampere at the emitter terminal. That emitter current will obviously produce a change in collector current. Now, we are discussing about the common base amplifier. In a common base amplifier, the current gain approximately equal to 1. Hence, output collector current is exactly equal to the input current which is I. Hence, the collector current magnitude is also equal to 1 milliamp. So, if I connect the load resistor with a magnitude of 5 kilo ohms, load resistance with a magnitude of 5 kilo ohms, then the amount of collector current which is passing through that load resistor 5 kilo ohm can have a voltage drop which is 5 volts. Now 0.1 volt change, so we applied a 0.1 volt at the input. The change in input voltage is 0.1 volt, but we have achieved a large amount of output voltage which is 5 volts. So amount of change in input voltage, small amount of change in input voltage can lead to the high amount of output voltage. Hence, it is a voltage amplifier. So the voltage level of the signal is amplified from input to output. Hence, these amplifiers are known as small signal amplifiers or the voltage amplifiers. Is it clear, everybody? Yes? Is it clear, everybody? Why we call this as a voltage amplifier? So I'm asking you a question. Please respond, Nana. Why we call these are voltage amplifiers? Simple definition. A small change in the input voltage can cause a large amount of change output voltage. The change in output voltage is large at the output, hence it is termed as voltage amplifiers. Is it clear, everybody? Right. Next slide will be our transistor. So CV is over. We'll move to our CE amplifier. Now in CE amplifier, like your CB, we connected the DC signals at input junction and output junction, which may forward bias input junction VBB, and which may reverse bias your output junction by the magnitude of VCC. Whereas in auto amplify, the smallest applied input signal, we are applying a voltage source Vs. We are calling it as a signal source. So Vs, so which is coupled through a coupling capacitor to the input terminal of your transistor. Now in your common emitter configuration, this is the input terminal. Hence we coupled your source Vs in series with a input terminal of the base of your common emitter configuration. And why we coupled your capacitor is in order to block the DC signals which comes from your signal source. So additional if any additional DC signals in your signal source, that can be blocked. So if I am having a DC signal, an additional DC signals which I am coupling to the base, so that can disturb the operating point of your amplifier, which may transfer that operating point towards the saturation or towards the cutoff region. Hence, in order to avoid that, so we are connecting a coupling capacitor, so which will be denoted with CC. So coupling capacitor with the CC. Now, so this can block how it can block the DC, since the reactance offered by the capacitor XC is equal to 1 by 2 pi Fc. So if I am applying a DC signal, so it's simply acting like a open circuit. So for a DC signal, apply 2 pi Fc. So now if my frequency of DC signal is 0, so if I have a DC signal at my input, that frequency becomes 0, reactance offered by the capacitor become infinite. So almost it is acting like a open circuit. Like that, we can block the DC signal and we can allow only AC signals to the input of your the base of your common emitter amplifier. Since that, we couple your input source through a coupling capacitor, as well as we'll also collect the output by connecting a coupling capacitor at the output terminal of your transistor. So hence, here we require the coupling capacitors to connect the input as well as to collect the output. Right. So now, so we have here an amplifier which by just observing its characteristics, we have to note down some characteristics of the amplifier, and those characteristics which are included with the input resistance, output resistance, gain, current gain, voltage gain, and power gain. So how to calculate the input resistance of your common emitter amplifier? Now, as we already I mentioned in the last class, that input resistance is the ratio of it. By definition, we could say that. So here we have to take the ratio of the change in input voltage with respect to the change in input current. So here in your common emitter amplifier, so change in VB with respect to the change in base current IB can give the input resistance. Next, output resistance. How to calculate the output resistance? The output resistance of a transistor amplifier, so common emitter amplifier, is high since the collector current changes slightly with the change in collector to emitter voltage. So by definition, we could say that output resistance is the ratio of change in output voltage with respect to the output current, change in output current. So R naught is equal to change in VCE with respect to your change in collector current. Now, in order to find the power gain as well as your voltage gain, so we have to calculate the effective collector load. Now, at the collector terminal, we are connecting your collector resistance RC in order to couple your VCC, whereas we'll collect your output voltage by connecting a load resistor RL at the output terminal of your transistor. Now, the output resistance of your transistor, so your output resistance of your transistor R naught can act like a load resistor. So now, in order to find the effective collector load, we have to take the effective collector load resistor value by taking the parallel combination of RC with respect to your R naught. Now, so here collector load resistor, effective collector load resistor is parallel combination of RC and output resistance of R naught, where the R naught is very high. So since the collector current doesn't depend on your collector to emitter voltage change, hence here now when your R naught is high in a parallel combination of RC and R naught, if I have a smallest value which is parallelly connected with your highest value, the combination of the parallel combination is ultimately equal to the lowest value. So output or effective collector load is approximately equal to RC if R naught is high. So now this is for only for single stage amplifier. Now how to calculate the output resistance, the effective load for the multi-stage amplifier is, so effective load is calculated by taking the parallel combination of RC R naught as well as the input resistance of the second stage. So in a multi-stage amplifier, we have to cascade. So cascade the more number of same stages like your CE stages, we have to connect it. So now the effective load is calculated by taking the parallel combination of RC, R naught and RA, where RA is the input resistance of second stage of the amplifier in a multi-stage amplifier. As we already discussed now, RC in parallel with R naught is approximately equal to RC. Hence, in a multi-stage amplifier or a two-stage amplifier, two-stage cascaded amplifier, that effective collector load is the parallel combination of RC and RA. Now, the current gain beta is change in collector current to the change in input current, and it is denoted with a beta, and it ranges from 20 to 500, which doesn't have any units. We got say collector current gain. So your current gain indicates that the input current becomes beta times of its collector current or the output current. Next, so in a common emitter amplifier, so we should also calculate the voltage gain, and the voltage gain is, by definition, we could say that it is the ratio of output voltage to the input voltage, where the change in output voltage is calculated by taking the product of your change in output current to the effective load. And change in input voltage VBE is calculated by calculating or taking the product of your change in input current with respect to your input resistance. Now here in your common emitter amplifier, change in output current is delta IC and effective load is RAC. So change in input current is delta IB and input resistance is RA. As we already know that, so the ratio of change in IC with respect to change in IB is equal to beta. Hence it is equal to beta into RAC divided by RI. So for a single stage amplifier, your RAC is equal to RC. Hence it is equal to beta into RC divided by RI. But for a multi-stage amplifier, this RAC is replaced with RC into RI divided by RC plus of RI, where RI is the input resistance of the second stage amplifier. Next, power gain. How to calculate a power gain in a common emitter amplifier. So we have to take the ratio of your output power to input power. Now output power is equal to, so IC square, output collector current IC square into of RAC, and input power is equal to IB square into input resistance. So IC square into RAC divided by IB square into RI. Now this is equal to beta current gain into of, and this is equal to the voltage gain. So let us denote that with the voltage gain. So as we already know that, here just look it out here. So IC into RAC divided by IB into RI, IB into RI is voltage gain AB. Now I am replacing the same change in IC into RAC divided by change in IB into RI. Hence the power gain AP is equal to beta, you can also write it as the current gain AI into of AB. So it is the product of current gain and voltage gain, gives you the power gain of your common emitter amplifier. Next, we'll move to your next slide with the transistor at how the transistor is acting at a low frequency. So now we'll move to the AC analysis. So till the previous slide, is it clear everybody? How to calculate the parameters of your common emitter amplifier? Is it clear everybody? Yes? Do you have any doubts? Next, I will move to the next slide. In this next slide, we are going to learn about the AC analysis of a amplifier. And this AC analysis is described using a two-port network, and we analyze those circuits using your hybrid parameter model, and will determine your H parameters and how to convert, what are the conversions of your H parameters. Next, generalized analysis of transistor amplifiers model using your H parameters. Next, analysis of the three amplifiers CB, CE, CC using your exact and approximate analysis. And the last one, comparisons of your transistor amplifiers. Now, everybody observe carefully here. In this slide, we are going to replace your transistor with a simple black box with the three terminals. So 1, 2, and the third terminal will be the common terminal. As I already explained, why I am taking the 4 terminals here. In order to obtain a 2-port network, we require 2 terminals at the input, 2 terminals at the output. So input side, I am taking the 2 terminals as 1, another one with a 1 dash. Output terminals, I am taking it as a 2 and 2 dash. Now, in a transistor, we have 3 terminals. So each terminal, if I am taking a common, so then we would have here 3 configurations and 3 amplifier or 3 amplifiers: common base, common emitter, common collector. Now here these H parameters or the hybrid parameters are derived based on the dependent sources and independent sources. Here, let I am taking the dependent sources and independent sources. Now, in a 2-port network or in a H parameter model, the input current and the output voltage are independent variables, and the input voltage as well as the output current are dependent variables. Now I am taking I1 and V2. Here I mentioned here II are the input current and your output voltage V0, II and V0 are independent variables, whereas input voltage Vi and your output current I0 are the dependent variables. Like that we have to take it, and we will take the relation between your parameters, H parameters. Now, here in your hybrid parameter or small signal equivalent circuit, so here, so H11, so 11 means, so this is the parameter which is calculated in the input side. H12, this is a parameter which is calculated from input to output, and H21 is the parameter which we calculate from output to input. H22 is the parameter which we only calculate at the output side. Is it clear, everybody? Yes or no? Is it clear? Yes, please respond, Mana. Is it clear, everybody? Right. So now I wanted to ask you a question. Which are the independent variables and which are the dependent variables? Anyone can answer? Tell me more. Which are the dependent variables in a 2-port network, and which parameters are independent variables? Right, I will repeat once again. Listen properly. Mhm. Are you able to see the screen? Yes? So, AC analysis of any amplifier, small signal analysis can be done with the two-port network, as the transistor is having 3 terminals. So in order to obtain the 4 terminals in a two-port network, so we are taking one terminal of transistor as common terminal, and now here, so we connected 1 dash are the input terminals, 2 dash are the output terminal. So as one of the terminal is connected with the ground. So now here in this transistor, we are defining the parameters by using two are taking as independent variables and two are taking out as a dependent variables. Now here the input current and output voltage of any amplifier can be taken as independent variables, where the input voltage and output current are taking it as a dependent variables. And these are the parameters. H11 is the input parameter, determine input to output. Next, H21 is the parameter which is determined from output to input, and H22 are the parameter is the parameter which is calculated at the output loop only. Hence here, so H11 is the input impedance which is denoted with HI. You can also write H11 with HI, H12 with the HR, H21 with HF, H22 with H0. H11 is the input impedance, H12 is the reverse transfer voltage ratio, H21 is the forward transfer current gain, so which is denoted with HF, and H22 is the output. Admittance H0. Now, so each parameter how to calculate, and that we are going to discuss in the discussion. So this is a simple project for input and output terminals equivalent to
Goblin.
And the Thevenin equivalent resistance at the side, and at the outer side, going to replace the terminal functioned with the admit. So the amplifier two-port network is replaced with the Thevenin equivalent voltage source and Thevenin resistance at the input. And at the output, we are replacing this source with a in shunt with a not on equivalent resistance H0. Now here, so this is the as a subscript we have mentioned. HI means it's the input resistance. HR means reverse voltage transfer function. HF means forward current gain. Next, H0 is the output admittance. Now, so after this first letter I, if I mention E means, so this is the H parameter equivalent model of your hybrid parameter model for common emitter configuration. So the second letter, if I mention with a B, so then that indicates the hybrid equivalent model for common base. So if I mention the second letter with a C, then it would be a common collector configuration. Now here, now I am taking a common base bias mode here. Now the amount of current flow in a transistor configuration, common base configuration, IE NPN transistor, and the collector current and the directions of your input current IB, base current IB. So base voltage is VE, input voltage VBE, and output voltage VCB. Next, so this is your simple model. So as I already mentioned, H11 with the HI, H12 with HR, H21 with HR, H22 with H0. Now, so here H11. Next, H parameters. So how to calculate the H parameters? Now, in order to find the input impedance, so we have to short circuit the output voltage. So output V0 must be short circuited. Next, in order to find, so your H12, so your reverse voltage gain. So we have to open circuit. We have to open circuit the input terminal. Then the input current is to 0. Now to find your current gain, forward current gain, short circuit the output. Short circuit your output terminals at the output port. Then we have here the H parameter, which is forward current gain I0 by II. So in order to find the admittance, output admittance H22, so you have to open circuit the input terminals. So then our input current becomes 0. Then we can find your output admittance. Now the units for input resistance is ohms, and your admittance is in mhos. So next we have here the reverse voltage gain and your forward current gain, which doesn't have any units. So these are represented with the numerical values. Now is it clear, everybody? So H11 is the input resistance, H12 is the reverse transfer voltage, and H21 is the forward transfer current. H22 is the output admittance. Now these are the methods how to calculate your input resistance, reverse voltage gain, as well as your forward current gain and output admittance. So now open circuited here we shorted your output terminals, then we obtain your input resistance as well as your reverse voltage gain. Whereas here in the second slide, sorry, in the second image, so in order to obtain your forward current gain, V0 must be, so output voltage source must be open circuited, and to find your output admittance, so we have to short circuit your, open circuit your input terminal. So hence here we have H22 equal to, so actually this is II, not I0. Next. So this is a simple hybrid equivalent model. So emitter is common emitter configuration, it is input current is IB, output current is collector current IC. So input loop is replaced with resistance in series with a voltage source, and the magnitude of that resistance is equal to HIE. So here the voltage source magnitude is equal to HRE into VCE, where HRE is the reverse voltage gain and VC is the output voltage of common emitter configuration. Next, a current source we replaced with a HFE, forward current gain, into the input base current, and with initial with a output admittance H0E. Now, so these are the parameters of the three configurations or three amplifiers. So this is your common emitter. So our dependent variables are VB, which is input voltage. VB, base voltage, is the input voltage in common emitter, and output collector is the collector current. So IC is the dependent variables, and independent variables are input current and here output voltage VC. So HIE is the input resistance, HRE is the reverse voltage gain, HFE is the forward current gain, and H0 is the output admittance. The same manner, in common collector configuration, our input is base and your output is your collector terminals. So hence here the independent variables are base current, input current, and output voltage. Common collector, we are collecting the output at emitter, hence it is VE. So next, dependent variables are your input voltage and your output current. So here IE. So VB equal to HIC into IB plus HRC into VE, and output current IE is equal to HFC IB plus H0C into VE. In common base configuration, so common base, emitter is the input and collector is the output terminal. Hence here the independent variables are input current and output voltage. So input current is IE and output voltage is VC. Next, dependent variables are output voltage and your output current. So here now, input voltage and output current. So input voltage is VE is equal to HIB IE plus HRB VC, and IC is equal to HFB IE plus H0B VC. Next, so in the next class we are going to do with the comparison, as well as we are going to analyze the each parameter, how to calculate in each configuration, and what was the relation between the parameters, H parameters, and how to calculate the overall voltage gains and overall current gain, as well as input resistance and output resistance. In addition, with those topics of hybrid parameter analysis, we are going to do with the gain bandwidth product and frequency response of your the AC response of your AC analysis of your amplifier. So CA amplifier AC analysis by applying what is the behavior of your amplifier at low frequency and at high frequency end. So those are all the topics. We'll clear it in your next session. So now I'm going to conduct the quiz. I'll start your quiz. Just answer the quiz and you can log out.